So this is part 5 of the unit involving the study of the structure of simple solids, where we're going to look at the close packing of spheres. More especially this can apply to metallic bonding. So there are a number of different ways in which, if we assume that atoms are spherical in nature, so they are spheres, then we can see how it is that they pack. Okay, so the first example that we look at is something called cubic pact, and you can see that the spheres pack in the shape of a cube, and there are quite a significant number of holes. So you can see there's holes here, there, any large space between the cubes, between the spheres, I beg your pardon, doesn't really involve very much efficient packing. Okay, so this is the first time that we see something like this. It's called cubic pact. Okay, the second example is hexagonal close pact. Now what we do is we take these cubes and we actually shift one of them into the hole that is created over here. Okay, let me just erase the previous drawings. Okay, and what we do is we take this sphere and we shift it into the hole there, there, and there, so that what you get is you see that now there's the first layer. This is the first layer, second layer, third layer, fourth layer. You now see that the second layer is shifted into that space, and as a result what you then get to see is that you can almost see a perfect hexagon forming, and we call this hexagonal close packing, HCC. All right, now how do these formations work? Okay, well, let's have a look. If we look first at diagram A, which is this one over here, this is diagram A, we have a single close packed layer, and it's a single hexagonal close packed layer because, as you can see, here is the hexagon shape, so it's hexagonal close packing. All right, now we want to stack another layer on top. So what we do, can you see there are holes here? All right, we stack the next layer on top of those holes. So this is what will happen in diagram B over here. We have a second close packed layer where we fill the gaps in the holes, and these lie in the dips above layer A. All right, and then what we can do, you can still see that in this diagram we still have a few holes. There's a hole here and a hole here. So on the next layer we can then take those ones, and the next A layer, for example, we can pack on top of the other atoms. So let me just, I've made a mistake, I beg your pardon. Let me just remove this. What we need to do, you can see that there's the next sphere over here is this one that I'm highlighting here, and then if we're going to hexagonally close pack spheres, then you can see that the next A layer will go on top of the layer below. Okay, so in diagram C we have a third A layer. It gives us an AB type structure, which is hexagonal close packing, and the top A layer is identical to the bottom A layer. All right, we have another example in number D over here, where you will still see that there are holes in the structure. Can you see there's a hole here, there are holes here, and holes here? So what we can do is we can take a third layer and we can fill those gaps in the B layer. Okay, so we cover those holes. They're not in the same, so the C layer is not in the same orientation as the A layer originally was. Okay, and what we then find is we then have this ABC repeating structure. This is called a cubic close packed arrangement, or as I will show you shortly in a few more slides time, the face-centered cubic. All right, so if we had to look at the top view and pick any one of the atoms that we see, so remember, if we see this particular atom over here, it can correspond to this atom over here because it has 6 atoms around it. Okay, I'm just marking those for you here like this. There are 6 atoms around it, and you can see there are 6 atoms around it here. 1, 2, 3, 4, 5, 6. Okay. At any one time above, there are 3 atoms above that central X layer and 3 atoms directly below, and their orientation is the same. So the triangle here is the same as the triangle here. This is A, B, A, B, A, B, otherwise known as hexagonal close packing. Sorry, excuse me. With the cubic close packing, what happens is that the bottom layer, if this was A and this was B, this is now C. And you can see that the orientation of the triangle here is not the same as the orientation of the triangle over here. All right. In each case, the coordination number is 12. Okay, so for a hexagonally close packed material, or for a face-centered cubic or cubic close packed material, the coordination number is 12, and you can see from the central red atom, if you count the number of atoms that are bonded to that central atom, that you should count 12 atoms. Okay, so there are 6 around the equatorial positions, and then these other positions that stick out, there are another 6, which makes 12. Okay, in this diagram on the right-hand side over here, you just see a better representation of the A, B packing, and then of course on the far right you will see the ABC, which is cubic close packed. This is otherwise known as face-centered cubic as well. I will show you in a slide shortly how we get to that. Okay, for a hexagonal close packed structure, this AB, the total number of atoms in the unit cell is 6. Okay, so how do we get that? I want you to look at this diagram on the bottom left over here. I'm marking it with a star at the moment. And I want you to look and I want you to see that we have 1, 2, 3, 4, 5, 6 atoms on those corners, okay, and another 6 at the bottom. 1, 2, 3, 4, 5, 6 on corners. Okay, now remember that corners means that they are contributing to only 1/6 of their value. There are 12 of them times 1/6, so that gives us 2. Okay, then we've got 1 on the face. Let me change the pen color. So 2, we've got an atom on a face and another atom on a face, so that contributes 2 atoms of a half each, so that is 1. And then finally we have 3 atoms on the inside. Let me just pick another color. We've got this one, and this one. Those are inside the whole unit cell. We've classified this as a whole unit cell. It's not a primitive unit cell, but it still is a unit cell. It's a hexagonal unit cell. So we have 3 on the inside. Sorry, excuse me. And we see then that we have 3 plus 2 plus 1 gives us 6 atoms in the hexagonal unit cell. Okay, so I'm going to write that this is a hexagonal unit cell. It's not a conventional primitive unit cell. Okay. The conventional primitive unit cell can be seen if you look at the diagram on the bottom right that I've drawn on. You can see the primitive unit cell by the dark lines. You should be able to see the cube. Okay, the lattice points for a hexagonal close packed structure has lattice points 0, 0, 0, and 1/3, 2/3, 1/2. I don't expect you to know how to calculate the lattice points for a non-primitive unit cell. Okay, angles are 90 degrees and 120 degrees. The coordination number is 12, which I've already shown you, and the packing efficiency, which you will have learned to do, is the same as for a face-centered cubic cell at 74%. Okay, so here is another way to just view the hexagonal close packing and the cubic close packing. I've shown you the hexagonal close packing, and I've shown you how to determine the number of atoms in the unit cell. This is a non-primitive unit cell. Okay, as it stands, it's non-primitive, but it helps us to determine how many atoms if are present in the unit cell, remembering that atoms are on the corners, 2 are on the faces, and 3 are inside. Okay, now as you can see, let's move over to the face-centered cubic one, or the cubic close pack. Have a look at the diagram at the bottom. You should notice the 3 different colors, and each of the layers, so this is layer A, this is layer B, and this will be layer C. Okay, and you see that the B layer fits into the gaps of the A layer, and the C layer fits into the gaps of the B layer. Now it's positioned in such a way that you can see that it's face-centered cubic. Okay, so if I quickly remove my drawings, you should be able to see that I will just annotate again that this, 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 and this form the faces of a cube. Okay, so there is the top face, and I've drawn you the front face, and then this atom here sits on a face, this atom here sits on a face. So it happens to be face-centered cubic. All right, the next slide shows you how we got this. Okay, so these 3 diagrams here show you for hexagonal close packed structures how the layers work, how they fit together. You can see that when the orientation of the A layer at the top here is identical to the layer at the bottom, and the B layer is shifted such that the B layer fits into the hole in that structure, so that you end up with this material, this packing over here. Okay, and if you look at it from the top, then you should see what it looks like from the top. But this gives you a cubic structure. I've already explained how the cube forms here. And then on the right hand side, if we looked at these 3, you can see how the cubic close packing works, or the face-centered cubic structures, where we've got layer A, B, and C. So white is layer A, the teal green is layer B, and the pink magenta is layer C, and they all fit into the holes. And when it's compressed together, this is what we get. When we turn it on its side, okay, so here is the axis, you can see the axis. When we turn it on its side so that we get this, you can see the face of the cube drawn in yellow. So hopefully this has helped you to understand the different types of packing. Quick refresh, there are 3 types. Cubic packing, which is the least efficient in terms of packing, where there's large holes between the spheres. And then we have hexagonal close packing and cubic close packing. And cubic close packing results in face-centered cubic arrangements.